have one more thing to talk about with radicals or square roots. And I want to go back to that idea from the beginning of our discussion of square roots, where we said if we take the square root of a negative, like square root of -9, we can't actually do that. We say that's not a real number. There is no real number, no number on the number line, that when we square it, we'll end up with a negative. In some cases, it's actually helpful to define what we're going to call imaginary units or imaginary numbers. And so the idea is we're just going to expand the view of our number system and basically say, well, what if we could take the square root of a negative? What would that look like? So far this semester, we have only been considering what we call real numbers. Real numbers are things that you could graph on a number line. So most of the numbers you've probably ever worked with have been real numbers. Now, we can have what we call imaginary numbers. And imaginary numbers involve square roots of negatives. They don't exist on our number line, but we're going to pretend, well, what if we could take the square root of a negative number? Altogether, both our real numbers and our imaginary numbers and any combination of real and imaginary numbers, we're going to call complex numbers. And so in this lesson, we're going to be thinking about the complex number system, both real numbers and imaginary numbers. And so to start, we have to define what's called the imaginary unit I. So we're going to use the letter I to stand for the square root of -1. That means I squared is going to be defined as -1. So we're going to define I to be some imaginary number that when you square it, you end up with -1. So I know this is really abstract. In this course, we have to think of this as really just like a thought exercise. We're just kind of stretching our minds a little bit when it comes to square roots. If you continue with math, you'll probably talk about complex numbers a little bit more. They do actually have some practical applications. Unfortunately, they don't come up until you get into a much kind of higher level of math. But I'd be happy to talk to you about any of you about that outside of class. So in terms of what do we need to know in this course, I want you to be able to write numbers using this imaginary unit I. So square root of -4, we can use a strategy very similar to when we simplified radicals. I can think of this as square root of 4 times -1. -4 is 4 times -1. So now I've got square root of 4 times square root of -1. I know that square root of 4 is 2, and I just defined square root of -1 to be I. So square root of -4 turns into the imaginary number 2I. In fact, anytime you have a negative underneath a radical, you can kind of think of it as turning into an I. So in example B, square root of -10, I'm going to think of that as square root of 10 times -1. So I've got root 10 times root -1. I cannot simplify that square root of 10, so that just stays as root 10. But my square root of -1 turns into an I. So example B is root 10 I. The negative just turns into the I. Finally, in example C, let's see, we've got a 5 plus, the negative turns into an I, and root 3 is 9. So I'm going to say square root of -9 is 3I. And this is as far as we can go. These are not like terms or like radicals, so we can't go any further with that complex number. So this number has a real part, the 5, and an imaginary part, the 3. So anytime we have a negative inside the square root, we're going to get that imaginary unit I. And so the next thing I want to talk about is some of the operations we can do with complex numbers. We'll start with addition and subtraction. And the idea is you can only add the real parts, and you can only add the imaginary parts. And so when you add or subtract complex numbers, it's a lot like combining like terms. You add the i's together and the numbers without i's together. So 3i plus 5i is 8i, minus 4 plus 7 is 3. And that's my answer. The same is true with subtraction, although don't forget that that negative applies to both the 5 and the minus 3i. So minus a minus 3i becomes a plus 3i. Combine like terms, we're left with a 4i minus 7. So both of these numbers have both a real part and imaginary part. Now when it comes to multiplication, we can use the same kind of properties we've used in the past. We can distribute, we can use FOIL. There's just going to be one difference. We're going to have to simplify our number when we're done multiplying. And I'll show you what I mean by that with some examples. So in example A, I'm going to distribute. 2i times 5i would be 10i squared. And 2i times 4 is 8i. So I multiply like I normally do. But then, if we defined I to be the square root of negative 1, I squared should be negative 1. So anywhere I see an I squared, I am just going to replace that with a negative 1. So this is actually 10 times negative 1 plus 8i, or negative 10 plus 8i. So the multiplication should look very familiar to what you've done in the past. The new part is if you see an I squared, you have to replace that with a negative 1. So in example B, this is a FOIL problem. My first would be 3i squared. Outer is 6i, inner is minus 5i, and last is minus 10. I'm going to replace that I squared with a negative 1. And then I'll have to go through and combine like terms. So we've got negative 3 plus 6i minus 5i minus 10. That turns into a negative 13 plus 1i. Now when it comes to division, we're going to have to do something that is pretty similar to that rationalizing the denominator that we talked about a couple lessons ago. So if there's only one term in the denominator, like in example A, the concept is we want to get rid of those i's in the denominator. And so to do that, I am going to multiply top and bottom by I. This will always work if you just have one term with an I in the denominator. So that's going to give me 6i over 2i squared. And then your I squared turns into a negative 1. So I've got 6i divided by negative 2. That's a negative 3i. You could have canceled out the 2 first and then multiplied by I. The order of those operations doesn't matter. Now in example B, our denominator has 2 terms. There's an I plus 2. And so just multiplying by I is actually not going to get rid of the i's in the denominator. Instead, we're going to have to multiply by what's called the conjugate. And the conjugate basically is something that takes advantage of that difference of squares formula. So in general, if your denominator is of the form a plus bi, so 2 terms, you are going to multiply by a minus bi. So the conjugate is basically the same thing with the opposite sign. So let me show you what I mean by that with this next example. My denominator is I plus 2, so I'm just going to change the sign in between them. And I'm going to multiply the top and bottom by I minus 2. So that would be my conjugate. Now in the numerator, I'm going to distribute, so I've got 4i minus 8, and then I could use FOIL or my difference of squares formula to multiply. And in fact, anytime you multiply by the conjugate, you can always use that difference of squares to multiply. That's actually why multiplying by the conjugate works in these problems. So what I mean by that is I plus 2 times I minus 2 should become an I squared minus 4. And then to finish, we are going to replace that I squared with a negative 1. So my denominator is negative 1 minus 4, or negative 5. So the idea behind division with complex numbers is you want to get rid of the i's in the denominator. You're rationalizing the denominator. I don't care if you leave your answer like this, although you could also write this as a negative 4 over 5i, 4 divided by negative 5, and then negative 8 divided by negative 5 would be a plus 8/5. So you can write your answer either way. All right, that's it for this lesson. Please let me know if you have any questions.